Imagine that you are looking at a light in a mirror. The light is the object. So here we have a picture of that situation. We have an object, and then we see a reflection of that object in the mirror. The reflection is known as the image. So the distance that the light is from the mirror, the distance from the object to the mirror surface, is known as the object distance. The image appears behind the mirror. It shows up in mirror land, and the distance that the image is from the mirror is known as the image distance. So here is a diagram showing what is happening. You have light coming from the object, and the light from the object reflects off the mirrors. If you see the light reflecting off the mirror, then your brain traces that light back to where the rays of light meet, and that's where you see an image. So we have an object, the actual thing that the light is coming from, and then we have an image that shows up as a reflection in our mirror. Now there are two kinds of images possible that you can get with mirrors. One is a real image. For a real image, light actually passes through the image point. It actually passes through the point where you see the image in the mirror. You can see an image on a screen that is placed at that point. So real images can be projected onto screens. A virtual image is one where light only appears to be coming from the image point. It's reflected off the mirror and can be traced back to find the image point, but light doesn't actually pass through that image point. So anytime you are looking at a flat mirror, what you are seeing is a virtual image. So if we look at the diagram again on the previous slide, we can see that the light rays reflect off the surface of the mirror. They don't actually pass through the image point. Your brain has traced those rays back, and so you see an image in the mirror at that location, but the light rays don't actually go there. So this would be a virtual image, and all images in flat mirrors are virtual images. Now, when we are analyzing the images made by mirrors, we draw what's called a ray diagram, where we trace the path that light would go from the object to the mirror and getting reflected off the mirror, and then how those light rays can be analyzed in order to find out where the image is located. So the standard way of doing that is to first off draw the surface of the mirror and then show where the object is located. And we represent the object as an upright arrow, and that object is some object distance away from the mirror. Then we draw at least two reflecting rays, usually from the tip of the object. So if you have an object, light scatters off this object and it goes in all directions. But of course, we're most interested in the light that goes from the object and then gets reflected off the surface of the mirror. So we'll draw a couple of representative light rays. So for example, a light ray going in a direction that's normal to the surface of this flat mirror will be reflected directly backward. And a light ray that makes some angle here is going to reflect off the mirror, and since the angle of incidence is equal to the angle of reflection, it will go this way. Now if we take these reflected rays, so this ray that's bounced off the mirror and this ray that's bounced off the mirror, and then we trace them back, we can see that they both appear to have come from this point. And so someone looking in the mirror will see an image that is located at this distance, S prime, from the surface of the mirror. So where those dashed lines intersect is where the object appears. So there's certain symbols that we use for some of the things involved in our ray diagram. S, as we've mentioned before, is the object distance, the distance of the object from the surface of the mirror. S prime is the image distance, the distance from the surface of the mirror to where the image appears. Y is the object height, so it's the height of the original object, and Y prime is the image height. It's the height of the reflective image. So we can look at how the image is different from the object in terms of its height. The magnification that is made by a mirror is defined as being equal to the image height divided by the object height. For a flat mirror, m is equal to 1, meaning that the mirror does not magnify or shrink the image. So for flat mirror images, the object distance is equal to the image distance, and the image is unmagnified. It's upright. When you look at a reflection of yourself in a flat mirror, it's not upside down. And we also discussed how the image is virtual. So the image is unmagnified, upright, and virtual, and you will see an image of yourself as far away from the surface of the mirror as you are. So here's a question for you. In the picture that's shown, the image of the stone seen by observer 1 is at C. Where does the observer 2 see the image?